The goal of this exercise is to come up with an eigenvalue problem specifically for Bloch modes. And the form of that eigenvalue problem looks a lot like the eigenvalue problem for Maxwell's equations in general. It's just that rather than having the curl by itself, you have some extra terms here, minus jk. So pause the video and see if you can use this particularly helpful expression to reduce the eigenvalue problem for Maxwell into this eigenvalue problem specifically for Bloch modes. Let's get started. Our starting point is, of course, the eigenvalue problem for Maxwell's equation. So that's theta h equal to omega squared mu h. But now in our particular case, h has a certain form given by Bloch's theorem. It's exponential minus jkr, and then times a periodic function, which we'll call uk of r. So the question is, if we have this particular form of h and we substitute that in this eigenvalue problem, what's the eigenvalue problem that comes out? So let's have a closer look at our theta operator. Let's remind ourselves of the fact that theta is actually curl 1 over epsilon curl. And then the question is, what happens when we have a very specific form of the function that comes here? So the first thing which is relevant, of course, is trying to figure out if we just have the curl of h rather than the whole operator, so just the first element of that operator. If we have the curl of h, what happens? So the curl of h, that becomes the curl of exponential minus j kr uk of r. And let's see how we can expand that. The useful equation here from vector calculus is that if we have the curl of the product of a scalar field and a vector, so the curl of psi of a, that actually becomes the gradient of psi cross a plus psi and then the curl of a. So this is useful in our case because obviously the scalar function psi will be exponential minus jkr in case of Bloch modes, and the vector field a is uk of r. So the first thing we need to do, which you can do if you pause the video, is calculate the gradient of psi, because this is what we need in this formula. So for our particular form of our h field, calculate the gradient of psi. Right, let's see what happens. So the gradient of psi is actually the gradient of exponential minus jkr. And a gradient consists of 3 components. The first component is the partial derivative with respect to x of our function psi, and then the partial derivative with respect to y of that same function, and so on and so forth. But the first component is ddx of our function psi, which is exponential minus jkr. And then we have ddy of the same exponential, ddz of that same exponential. But because I'm lazy, I don't copy that here. Let's expand this a little bit because we don't have an x immediately here, but we should then therefore write this as ddx of, well, this exponential minus jkr. If we explicitly write down the different components, that becomes exponential minus jkxx times exponential minus jkyy, exponential minus jkzz, and then we have 2 more components. And here it becomes a little bit easier to calculate the derivative with respect to x. That simply gives us a prefactor exponential minus jkx. And then we still have that same thing over here. So let's write that more compactly as exponential minus jkr, exponential minus jkr. And now it becomes clear what will happen for the second component. When we take the derivative with respect to y, we get the following. And obviously, no big surprise here, exponential minus jkz, exponential minus jkr. Or we can write this more compactly. We can factor out exponential minus jkr, which is just a constant. We can bring that out. And then we just have minus j and then the factor k exponential minus jkr. So this is how we can calculate the gradient of psi and write down the result in a very compact way. So now we know this intermediate result. Perhaps you can pause here and use what we've learned to calculate the curl of H in case of Bloch modes. So let me copy the equation that we need again. So we had the curl of the product of a scalar and a vector. That was the gradient of that scalar cross product with A plus psi, and then the curl of A. Okay, we just calculated what the gradient of psi is. So we can calculate that the curl of our magnetic field is first of all the gradient of psi. So for the gradient of psi, that's going to be minus j k exponential minus j k r. So that's the gradient of psi, and we need to take the cross product with A, and in our case that was uk of r. Okay, so that's the first term. And then for the second term, we start off with psi, that's exponential minus jkr again. And then we have the curl of A, and the curl of A, that's going to be the curl of UK. So this is what the gradient, so this is what the curl of H is. We can actually simplify this a little bit. In both of the terms, we have exponential minus jkr. So this we can bring out in front. If we look at the back of these terms, we always have here this cross product with UK. So finally, we can simplify this as exponential minus jkr, which is a scalar we bring in front of the equation. And then we have minus jk plus the nabla operator cross product UK. So this is a more compact way of writing down exactly the same thing that we have here. So that's already an important step. We know what the curl of H is. Now the final thing we need to do, and you can pause the video to calculate that, is calculate the whole theta operator, which is curl 1 over epsilon curl. So just take the final step here and then figure out what the complete eigenvalue problem is. So we have our eigenvalue problem, theta of H, consisting of curl 1 over epsilon curl of H. And we just spent some time calculating what curl of H is. You can see the results right here. So that actually becomes the curl of 1 over epsilon. And then we copy and paste what we just spent a lot of blood, sweat, and tears to calculate. Exponential minus jkr minus jk plus nabla, and then uk. Good. Let's now do a very difficult manipulation. Let's just swap the order of these two scalars here. So epsilon is a scalar and exponential minus jkr is also a scalar. So we can write this down as the curl of exponential minus jkr. And then we have here 1 over epsilon minus jk plus nabla cross uk. And then you see basically that we're in a very similar situation as what we had before. we have the curl of something which is the product of a scalar function, psi, and it's actually the same psi as we had upstairs. It's again exponential minus jkr. And then we have a vector function, a, which in our previous application, when we just were calculating the curl of h, that was just uk. But now in this case, a is a bit more complicated. A is this whole mess over here. What we can basically do is we can just use the same equation that we had up there to calculate the curl of the product of psi and a. The only thing we need to do is in this particular equation, we need to replace uk, which was our previous a vector function, by our new a vector function, which is this whole mess over here. So let's just do that. And then finally, we end up with exponential minus jkr minus jk plus nabla. So here I'm just copying this thing to over here. And then the final thing I need to do is I need to replace this uk by this complicated expression over here, which is just 1 over epsilon, and then another curl that we already pre-calculated, minus jk plus nabla curl uk. And now we're basically almost there. The only thing we need to realize is that since this was an eigenvalue problem, we have that the theta operator operating upon h gives us omega squared mu of h. And in our case, h is actually given by exponential minus jkr uk. And here we have the final result, because we have this exponential minus jk over here. We also have it over there. And then finally, we end up with the eigenvalue problem for the periodic function uk, which is just minus jk plus the nabla operator 1 over epsilon, and then that same operator minus jk, like so, uk equal to omega squared, rather, equal to omega squared mu uk. So it looks very similar to the eigenvalue problem that we had earlier for the general case. The only difference is, rather than having a nabla operator here, we have nabla plus a second term. And if you take a step back, the existence of that second term is actually very obvious. It just comes from taking the derivative of exponential minus jkr here. Then you get this extra minus jk in front of the equation. So it was a rather lengthy calculation to make sure that we actually understood where this was coming from.